let's see, if I ask you to determine whether males or females, a population of males or females, I'm having trouble writing here, has different blood pressures, right? In other words, you sample 50 males, you sample 62 females from a random independent sample of 50 males and 62 females. And we want to predict whether or not this population of males has the same or different blood pressure than this population of females. What test would we use? Right? What are you going to analyze? What measurement of blood pressure are you comparing for the two groups? The mean, right? You want to know whether the means of these two groups is the same. Okay, so what are our variables here? Our variables are gender, right? What kind of variable is gender? It's categorical, right? It's category or a nominal, categorical or nominal, right? And what kind of variable is blood pressure? Right, it's scalar, numerical, whichever way you want to call it. Happens SPSS happens to call it scalar, but yeah, it's not an integer, because you usually see it described as an integer because nobody bothers to tell you what the decimal place is. In other words, somebody says your blood pressure is 120 over 180, 120 over 80. They don't bother to tell you that it's really 120.1976 over 80 point. In other words, it's a continuous scale. If you really used like a column of mercury and you really read the scale, or if you had an electronic one and you had the digits display to 7 decimal places, it would be a continuous number. But we usually see it as an integer, but it really isn't an integer. It's a continuous scale. Okay, so we have numerical variable, continuous numerical variable, integer or not, doesn't really matter, and we have a categorical variable. And what we're interested in doing is showing that there's a difference between the mean blood pressure for group A, for population A, and the mean blood pressure for population B. So we're comparing two means, and we use a t-test to compare two means, right? We set up our null hypothesis. That null hypothesis is that mu1 is equal to mu2. There's no difference in the means of the two groups, right? So if you happen to have in the data that you're analyzing two groups, and you wanted to analyze some a numerical variable like some titers of antigens for Ebola or something like that, and you wanted to you tested a whole bunch of people, randomly selected people from each of the two groups. You wanted to see if the mean for those two groups was the same or not. You would use a t-test. Okay, so that's a t-test. So that's a valuable test for us. We know in that situation we have something that will allow us to predict whether these two means for these two populations are different with a certain whatever level of certainty we want to assign. 95% certainty, alpha is equal to 0.05, 99% certainty, 99% certainty, and so on and so forth. Okay, now let's say I wanted to apply the same test for blood pressure across ethnic groups by ethnicity. What kind of variable is ethnicity? That's categorical also, right? Except the difference here is that instead of two genders, we're dealing with multiple ethnicities, right? So we have many groups that we want to compare. So now we're not comparing two means. We may be comparing 6 means. The means of 6 different groups: Hispanic, Black, White, Pacific Islander, so on and so forth, Asian, and so on and so forth. So we have multiple means. So what test have we learned that will allow us to quickly and effectively determine if there's a difference in the means of these groups, multiple groups? ANOVA, analysis of variance, right? And the way we would apply that is that first we'd apply analysis of variance to see if there's a difference between any of the means for the groups. And then if we found out that there was, if we could reject the null hypothesis, which now is that mu1 is equal to mu2 is equal to mu3 is equal to mu4, and so on and so forth, that there's no difference between the means. Well, now the analysis of variance will allow us to detect whether there is a difference between any of the means. Then we can do additional tests Remember, those were called post hoc tests to determine if there's a difference between any particular means. What particular means are different, if any of them are different. Okay, so if our analysis of variance allows us to reject the null hypothesis, then we have the evidence that we need to go ahead and do those post hoc tests and see where those differences are. If it doesn't allow us to reject the null hypothesis, well, basically that's telling us is that there really isn't a reliable difference between any of those means that will satisfy our criteria of alpha is equal to 0.05. Okay, so that's something that you might apply. If your data that you're going to work on in your project has a numerical variable, and there could be any number of numerical variables that you're dealing with, and they're broken up into more than two groups, and you want to compare the means of all of those groups at once, you're going to use analysis of variance. Okay, so what's missing here? What have we not covered? What kind of combinations of data have we not covered yet? How about if you have two categorical variables? Categorical and categorical variables, right? So where would that come up? I mean, what's a situation where that would come up? Well, let's look at the simplest situation. Say like where they're both binomial, they both have one value. Okay, so for instance, let's say we want to see if there's any association between gender and HIV status, right? What is gender? What kind of variable is gender? It's category, right? What kind of value? What kind of value is HIV status? Yes or no, right? Positive or negative? That's categorical also, right? Positive or negative, right? So we have two categorical variables. Now this gets a little bit complicated now because now we don't really have numbers to compare. We're not going to find the mean value for gender. We're not going to find the mean value for HIV status. Doesn't mean anything, right? However, we may know that that if we sample, let's say we went into the population that we're interested in, and we sampled 100 males, 100 females, 100 males, right? And out of those 100 females, we found that 20 of them were HIV positive and 80 of them were HIV negative. And then we sampled the males, and we found that 30 of them were HIV positive and 70, maybe they're drug users, a high risk population. 70 of them are HIV negative, right? Well, now we have a series of categories here. So we can see that, for females, the rate is 20%, right? Probability of a female in this population being HIV positive is 20%. Probability of a male being HIV positive is 30%. Now, is that different enough for you? Remember that this is our little P cap here. Remember, P cap is our sample proportion, right? P cap, right, approximates the real proportion for the entire population of female drug users or the entire population for male drug users, but it's not equal to it. It just approximates it. So we could have easily, instead, let's say 20 is the real proportion, we could have easily gotten 25 females out of 100 if it's that proportion, and we could have easily gotten 21 males instead of the true proportion of 30 when we took our sample. So there is a chance that we could be wrong. We could have this reversed. They could really be the same, and we think one is 20%, the other is 30%. So we need to analyze this in a way that we can predict what our level of certainty is that these differences are real. So we need a new statistic, right, is basically what I'm driving at. The statistics we know so far, the t-test, the confidence interval, the direct application of the confidence interval, and the analysis of variance, not going to work for us here because they're really set up for numerical variables, right? Now there is, technically you could say to yourself, well, P cap is equal to 20%, 0.20 for females, and P cap for males is equal to 30%. Well, maybe what I can do here, P cap females, males, maybe what I can do here is I can calculate a confidence interval for males, females, and males and see if they overlap, except that's kind of breaking the rule, isn't it? because there's a few issues there with, like, whether or not it's a two-sided analysis and a one-sided analysis. We really don't do, we only do that, use the confidence interval, when we're testing against a fixed value. Remember that one-sided, that one sample t-test, we basically was kind of a confidence interval almost, right? So we really can't do that. That's not really legal or proper for us to do. So we need some way to analyze this data. Okay, so that's going to involve a new statistic. And it's actually going to involve a few new statistics. It's going to involve something called chi-square. Chi is the Greek letter chi. It looks like a capital X, right? Squared. And we're going to use some. We're going to examine some other variables called relative risk or risk, and odds or odds ratio. We're going to understand what those things mean. Now, they just came up in the lecture, right? Those terms are not new. You've heard them about a half hour. I'm glad to see you're nodding and you actually remember them from about a half hour ago, right? Yeah. Can anybody explain to me what chi-square is? Yeah.
You're calculating how your observed values differ from your expected values. Like if you'd expect, so if you have two events and you're independent, you might expect that half to do one thing and half to do the other thing, but maybe it's like 60-40.
Okay, good. So you're looking to see if what you would expect to happen is really the same as what you actually observe when you do your sample. Okay, well, how about relative risk? Anybody remember how they define? Anybody else remember how they defined relative risk? Right. Well, what's risk? You go to church on Sunday, yeah, right? A lot of times they'll have like a little luncheon afterwards and stuff like that, right? So, like you have a little coleslaw, you have a little chicken salad, it's been sitting out for a little while, right? So maybe all of a sudden, there's 100 people at the church luncheon, and out of those 100 people, 30 of them get sick, right? Well, we could we could ask everybody, well, how many of you ate the coleslaw? How many of you ate the chicken salad? Anything with mayonnaise is church lunch, and don't eat it. Trust me. So who ate this stuff? Who ate that stuff? And you can say, well, gee, we 24 people ate this particular dish. Of them, 8 people got sick. So what was their risk of getting sick if they ate that? Well, it was 8 out of 24, right? That's kind of a pretty straightforward kind of analysis. It's kind of very intuitive, right? Your risk, 100 people ate it, 10 people got sick, then the risk is 10 out of 100. This coming year, let's say 15 out of every 100 people are going to get the flu, right? So your risk of getting the flu, assuming that you have the same, everybody's the same age and the same susceptibility, your group is all the same age, the same susceptibility. If your group has a likelihood of 15%, a prevalence of 15%, you would expect 15 out of 100 people to get the flu. That's called risk, or that's also called a rate or prevalence rate, right? Now, there's another number that you can use to communicate that, and that's called odds. Odds is a lot less intuitive, right? So, for instance, if you go to the track and you play the horses, right? You get odds of 4-1. If you bet $2, how much does that bet pay off? If you bet $2, pays off 4-1, pays off $8, right? So how does that work? Well, gee, it's 4-1, losing to winning. Basically, what those odds say, you also get your $2 back. What those odds say is that if the race will run 5 times, then the odds are predicting that the horse will win 4 times and lose once. That's different than lose 4 times and win once. That's different than rate, right? If you ran once, in other words, 4-1, right, or 1 win to 4 losses, that's like basically win 25% of the time. The odds are you're going to win 25% of the time, 20% of the time, right? 4 losses, 1 win. That's 20% of the time. That's your rate. But the odds are 4-1 or 1-4, which is 0.25, not 0.20. It's not quite as intuitive as rate is. So let's go back to our influenza example. 15% of the population, your group, is going to get influenza. That's the rate, that's the prevalence rate. What's the odds that you're going to get it? Well, it sounds like 15 out of every 100 are going to get it. 15 people are going to get it. 85 people are not going to get it. What are the odds of you getting it? It's 15 over 85. That's the odds of getting it. To not, the probability of getting it divided by the probability of not getting it. If you looked at the formula that you saw before, the fancier formula you saw before, it was the probability divided by 1 minus the probability of getting influenza divided by 1 minus the probability of getting influenza. Makes a lot less sense intuitively to us, right? But there's reasons why they like to use it in studies. I won't go into the reasons right now. We'll just go into the mechanics of how we're going to use it and so on and so forth. You can use them pretty interchangeably in a lot of cases. In fact, you can calculate one, convert one into the other. Okay, so but we'll worry about that later on, because right now we really need to understand how to apply this. Why do we need to apply this, right? Have you guys taken a look at the community health survey data, right? 99% of that data is what kind of data? Categorical, right? Did you notice that? There's very few selections in there that give you actual numbers, numerical data. There might be a few. There's weight, there's BMI, there's age, there's a few. There's maybe 5 or 10 pieces variables that are numerical, but there's 200 that are categories. In other words, have you ever been diagnosed with as having been told you have asthma? Yes or no, or didn't answer. Basically, it's, like no data, right? And this, have you ever? Are you frequently sad? Yes. Once a month, twice a month, every day, and so on. It's categories, right? So, our problem is that up until now, there's not much we could do with that data, right? So after today, we'll have tools for us to be able to use that categorical data and analyze it. Okay, so let's take a look at how we might handle that. And when we go through, I'm going to go through an example to start off with, and then I'm going to show you a way that you can download and use all of the raw data from the community health survey. Kind of get around that table that you're using, so you can actually get data that you can work with in SPSS or R and stuff like that. So let's go through this with one example. Then we'll look at what the data looks like on the community health survey, and you might have other pieces of data you want to work with as well. Okay, so now before I get into that, I just want to mention there's one other kind of situation that we haven't mentioned so far that you could run into that none of these tests, including what we're going to do today, will cover. Anybody? What combination of variable types have we not covered? We've gotten categorical, numerical. We've gotten categorical, categorical. What are we missing here? Ordinal is kind of like a version of categorical, but you're right. We didn't really get into that very specifically. But they're really kind of categories anyway, right? In a sense. How about numerical? Anybody know what you call it when you compare one numerical variable to another numerical variable? Bingo, correlation, right? I hate it when people have taken this course before and they know all the answers. But yeah, correlation. There's also something called regression, which is the ugly stepchild of correlation that we're going to learn about. It's going to be really nasty. Well, it's going to be a little nasty. It's not for some of you guys. It'll be a little bit difficult to understand, but for most of you guys, you'll be okay. And all of you will understand it once you get a chance to wrap your head around it. It's correlation. Well, what does that mean? Well, let me give you a correlation. Let me give you an idea of the difference. First of all, correlation is, and kind of what the difference between correlation and regression is. Correlation is when you look for an association between two numerical variables. For instance, let's say that we went into the New York City archives and we found that they have records on how many firemen went to a fire. Each fire, they have a number of firemen who responded to a fire, and the amount of property damage that took place at that fire. So let's see, 3 firemen responded here. Property damage $1,000. 50 firemen responded here. Property damage 2.5 million. 12 firemen responded here. Property damage 100,000. Right? Well, does it make sense to you that there's an association between the number of firemen responding and the amount of property damage a fire causes? Right? So if you actually plotted that and said, hey, I'm going to make an XY chart here, and the X is going to be the number of firemen on the x-axis is going to be number of firemen. On the y-axis, are going to put a dot by the amount of property damage. So you can almost imagine that there is, as the number of firemen goes up, these dots will line up so that the property damage goes up. Are the firemen causing the damage? Sometimes yes, right? It happens occasionally. They can be. You've ever seen them to respond to a fire? First thing they take out is that big axe. So sometimes yes, but most of the time it's the size of the fire that determines how many firemen go there, right? So there is a association. So our null hypothesis might have started. There's no association between number of firemen, but in fact we would expect there probably is. So there is an association between the number of firemen and the amount of property damage that occurs at a fire. So the fireman causing it? No. There's an association, but it's not a causality. Firemen are not the ones causing the damage. It just happens that they're also related to the same things, the size of the fire, both of them related to the size of the fire. Now, in some cases, you may have numerical variables where there is an association, right? So, for instance, you might have an association. Let's say we looked at, we took a number of people that are pre-diabetic, took 100 subjects that are pre-diabetic, and we fed them on various days, we fed them a different number of carbs each day, and we took their blood sugar. And we might find an association between the amount of carbs they ate and their blood sugar. More carbs, higher blood sugar, right? That is a causal association. We could kind of think maybe that's a causal association. The amount of carbs you're eating is related to your blood, the level of your blood sugar, right? A level of sugar in your blood. So in regression, we can find that we can apply a formula to that correlation or that causal relationship, so that formula can become predictive. We can use a formula to tell us, well, if we take a random individual that fits in this group pre-diabetic, if we feed them so many carbs, this is what we expect is going to be their blood sugar. So maybe we can make some decisions based on that. Like, in other words, maybe the American Diabetic Association did a study like that someday to help people determine if they're pre-diabetic, what level of carbs they should be eating and how they should be spreading it out over the day or something like that. Maybe somebody did a study like that. I don't know, but you get the idea. That correlation and regression are a new statistic that we're going to use to look to see if there's an association between two numerical variables. Is there an association between BMI and weight? Yeah, it's a perfect association. Why is it a perfect association? Because it's one of the elements of calculating a BMI. If one predicts the other, right? So actually you left out height, so it's not perfect predictor because height's involved too. But obviously more weight or shorter height, height. So there is a direct relationship between BMI and weight. So, but that's really one that's in the formula, because BMI is just a formula for height that combines height and weight. But there's a lot of hidden associations that when we analyze it, we can observe, and we can maybe might be useful to us to be able to know there's a real association and make it predictable. Okay, so let's go back to what we're going to do tonight, our categorical variable. So on Blackboard, so hidden somewhere on Blackboard, there is a file which looks something like this. I'm going to open it up in Excel. Okay, so this one is called 1B chi-square Excel 2. I'm not sure how it got so complicated. Okay, so let's say that we have a population that has a high rate of lung disease, or high rate of asbestos exposure and lung disease, and we sample this population, and we find we have 180 people. We sample the group we sample is 500 randomly selected individuals from this high risk population, and of those, maybe they're very heavy smokers and so on and so forth, have a lot of other exposures. Of those, 320 of them had no asbestos exposure, no significant asbestos exposure. So 70 out of those 320, it turns out, have lung disease, right? Maybe COPD, maybe some other, that's not really specific, but have some sort of lung impairment. Okay, so now of the people that do have asbestos exposure, right? 60 out of 100, there's 180 of those people that had asbestos exposure. In other words, they would take 500 randomly. Maybe these are people that worked at the Brooklyn Navy Yard in the 50s and 60s or something like that. And we find heavy smokers, a lot of asbestos exposure. They're elderly now, so high rates of lung disease probably not that uncommon. Okay, so we find that out of 100, when we questioned them, 180 of them said they had no asbestos exposure they knew of, and 60 of those had lung disease out of 180. Okay, so now let's take a look at the idea of what our risk for these two groups would be of having lung disease. Okay, so now again, remember when we were doing the diagnostic tests, we set the diagnostic tests up in a 2 by 2 table so that we can analyze that data. Remember we called that a contingency table, I think we called it, right? This is a contingency table. Also, SPSS uses the term crosstabs, right? Or horizontal and vertical tables. Okay. In general, it makes it a little bit more convenient if you put the exposure in the rows and the outcome, disease or not disease, in the columns. I like to put the positive exposure in the top row and the no exposure or lower exposure in the bottom row. Makes it a little easier for me to keep the numbers straight. Similarly, with the outcome, I like to put the disease group in the left column and the not disease group in the right column. Do you have to do it that way? No. Yeah, but I think you'll find it a little easier if you do it that way, especially when we're working with SPSS. It's going to be a little bit, the way it lays out the tables and stuff like that, going to make this a little bit more intuitive. Okay, so now remember how we defined risk. I'm going to look at this idea of risk. Another way of talking about this is just rate, risk or rate. Okay, so hang on just a second. How are you guys doing online? You okay? Can you still hear me, see me, feel me? Tommy, what was that? How was that? Like the who? Hear me, feel me, Tommy, right? Okay, let me make sure I muted everybody. Okay. Okay, good. Excellent. Just want to make sure you're still there. Okay, so I'm going to take a look at this idea of rate or risk. Kind of using the term interchangeably. Okay, so what's the risk or rate that people who are exposed to asbestos in this population, what's their risk or rate for getting lung cancer? It's going to be equal to, what would you say, 60 over, what do you think? 180, right? Okay, so their rate at which they're getting lung cancer, 60 out of 180, pretty clearly is 33%, right? Okay, and for people that weren't exposed, it's 70 out of 250. Okay, that's 28%. So it looks clear to me that there's a higher risk of the people that had the exposure than the people that didn't have the exposure. Okay, so now I'm going to make this, each one of these is the risk for this group, the risk for this group. I'm going to come up with a new number here. I'm going to call it relative risk, or RR, right? That's going to be relative risk, or risk rate. And when we're talking about a rate, we're almost always talking about a fraction, one thing divided by another thing, a numerator and a denominator. So my risk rate is going to be equal to the rate at which people that were exposed to asbestos have lung disease divided by the rate at which people who weren't exposed have lung disease. Now, if there's no association between asbestos exposure and lung disease, what would you expect that risk rate or relative rate to be equal to? 1. Makes sense, right? You would expect that people who has exposure have their rate would be 33%, let's say, and people who don't have an exposure would be 38% or 28% and 28%. You'd expect the risk for both of them, or the rate both of them are getting lung disease, would be the same, and that would be equal to 1. In this case, it's basically 1.2. right? Well, what does that tell us?
The risk rate of no is wrong. You divided 70 by 250 instead of
Oh, I'm
350.
sorry. Did I do that?
Yeah.
Okay. Yeah. Oh, I messed up. Okay. I should have been D5, D4.
D4.
You're absolutely right. There we go. 1.5 then, right? At least one of you guys caught that. Right? It's 60 over 180 and 70 over 320. Right? That's the rate. Okay. So now my relative risk or my relative rate or my rate, relative rate is 1.5, 1.5. What does that say to you? That says to you it's 1.5. Your risk of getting lung disease if you were exposed within this population and exposed to asbestos is 1.5 times if you didn't have that exposure. That's called relative risk, right? Or relative rate, RR. Okay, so now I'm going to take another. I'm going to look at another way of doing this. Okay, and that other way, I'm going to get rid of this over here. I'm going to look at in terms of odds. Okay, so let's look at odds. What were odds equal to again? Odds were equal to the probability of if you had the exposure times 1 minus the probability of your risk if you had the exposure. An easier way to think about that is to say 60 over, whoops, gotta put an equal sign in there, 60 over 120. Okay, so your odds are 50%, right? 0.5. 60 over 120. Right? So for every one person that has lung disease in this group, there are 2 people that don't have lung disease. For every 50 that have lung disease, there's 100 that don't have lung disease. Okay, a little bit different idea than this idea of risk or rate, right? So now, what about for the people that didn't have an exposure? What's that going to be equal to? 70 over 250. There you go. Okay, good. So now, just like before, I can calculate an odds ratio. If there's no association between asbestos exposure and a lung disease in this high risk population, what would we expect the odds ratio to be between exposed group and the unexposed group? We would expect it to be like the relative risk 1. We'd expect the same odds for both groups. And in fact, it comes up to be 1.78. Similar to what we got for relative risk, but it's a different calculation. There are ways to convert between one and the other, right? Because you can see that they're developed from the same raw data, right? But in this case, it's odds ratio. Now, remember we talked about we need a way to decide whether or not, since this is different than 1, right? We don't know for sure whether or not this difference than 1 is due to chance because it's a relatively small. It's a sample, right? So we don't know if it's really true of the entire population of everybody that worked in the Navy Yard in the 1950s or 60s. So we only know what we have from our sample. So we have to have a way to determine whether or not this is due to chance. So what do you think a good null hypothesis would be here? Let's just look at odds ratio now, because most studies tend to use odds ratio rather than risk or rate. Okay, so what's a null hypothesis? Null hypothesis would be that there is no association between asbestos exposure and lung cancer. And what would we expect the odds ratio to be in that case? 1. Okay, and our alternative hypothesis is that there is an association. Right? So what would the odds ratio be in that case?
Greater or less?
Yeah, it could be different, right? Exactly. It could be maybe asbestos is protective. I mean, if you didn't know anything about asbestos, it could very well be protective, right? So it's whatever it is, it's not 1. Now, there's a lot of ways we could look at this. One way is we could look at these as proportions, right? 0.5 and 0.28, and we know we could calculate confidence intervals and so on and so forth. We don't like to do that, right? We don't like to examine overlapping confidence interval, but we're pretty okay with developing a confidence interval and comparing that with a fixed number. So what we really want to know is what the confidence interval for the odds ratio is, or what the confidence interval for the relative risk is. And we want to make sure what number is not inside that confidence interval. 1, because if that number is not in that confidence interval, we're 95% certain that the relative risk of the odds ratio is not 1, is not a number that would suggest that there's no association between the exposure and the disease. So we're not gonna calculate odds ratio here, but we will calculate it later on when we work with SPSS. We're going to take this a step further. There's another statistic that we can use to understand whether or not there's an association between asbestos exposure and lung disease. Okay, and one of the things that we can see here is that we took a random sample of 500 people from this high risk population. I'm going to insert a row here so it makes it a little easier to see. Okay, and we noticed that 500 people were chosen randomly, right? So, whatever, this probably represents likely the proportion of each group within that population. How many people had exposure, how many didn't? What's the prevalence? What's the rate at which the entire population, not the ones that are exposed to asbestos, not exposed, the entire population, what do you think the prevalence of lung disease is in this population? How many people are in the population? How many people are in a sample? 500. How many people got lung disease in that sample of 500, right? Is 130. So what's our prevalence? Yeah, that sounds good to me, right? It's 130 divided by 500. Good. So that's 26% of this population has lung disease. Okay, so now I'm going to take a look at this population, just the sample that we took. How many people did we were in our survey had 108 had asbestos exposure? 180, right? And how many people didn't? 320. Okay, so I'm going to set up another table here. This table is going to represent if in fact there's no difference between asbestos exposure and no asbestos exposure, there's no association, right? Then what would I have expected this table to look like? So if we have 180 people chosen at random from this population, right, and there's no association between asbestos exposure and lung disease, how many people out of 180 would we expect to have lung disease? We'd expect what percentage of the 180 to have lung disease? The prevalence, right? In other words, the prevalence is 26% overall. So we'd expect 26% of these 180 people to have lung disease. So it's going to be 0.26 times 180. Okay, we'd expect 46.8 people, right? Obviously, you're never going to get 46.8 people. And interestingly enough, notice that in this table, we're going to wind up with fractional values. But we didn't wind up with fractional values in our exposed table because we can't. We counted people. We can't have 8/10 of a person in real life, right? That may come up later on when we start to talk about continuity and stuff like that. Okay. So, but down here, when I'm creating this table of what it should have looked like if there's no association, I'm likely going to have some fractional values. Okay. So now, out of 320, how many people would I expect to have lung disease? Equals 0.26 times 320. Okay, and how about not in that first group, asbestos exposure? What's going to be the difference between 180 and minus? Whoops, excuse me. 180 minus 46.8. Okay, and this is going to be equal to 320 minus 83.2. I could have also just done that by multiplying those numbers by 74%, 1 minus P, right? 1 minus the prevalence. Okay, everybody comfortable with that? Let's take a look at what our sums are. How many people have lung disease? Yeah, 130. Works out exactly right, right? Just what we would expect it, as we would expect, because we based it on the prevalence of the disease. Okay, so that works out okay too. So that's kind of a check on what we were doing. Okay, so now we're going to call these values up here our observed values. We're going to call these values down here our expected values, right? Now let me ask you something. If this was really true, that the prevalence was 26%, and you took a sample of this population, 180 people, 320 people, what do you think the odds would be just sampling that you would get exactly 60 people? Not very good, right? Or you'd get exactly 120 people with no lung disease in that group. That you'd get exactly what you would expect to get. Not very good, right? Because just because of sampling, sometimes you're gonna get fewer people that are in one group, more in another group, and so on and so forth. So there's a certain amount of error that's introduced just, but it's by chance, right? We've introduced chance by sampling. Okay, so we wouldn't expect to get exactly the same result. However, we also wouldn't expect to get drastically different results. We wouldn't expect to get, 0 and 140 or something like that for the number of people, right? That would be, outrageous, to think we might get some sort of result like that if the prevalence is really, if there really, no association and the prevalence was 26%. So we can kind of say to ourselves, you can kind of like intuitively say to yourself, you know, the bigger the difference between the observed values that I have and the expected values that I have, the less likely that the differences are due to chance. Okay? And what we're interested in is understanding how big the differences have to be between the table for the observed values and the expected values for us to be able to say with 95% certainty that the differences are not due to chance. In other words, reject our null hypothesis that there's no association between asbestos exposure and lung disease. Okay, so now let's invent a statistic to do this. Okay, so we're looking for the difference between these two values, between these two tables. How big a difference do we have between these two tables? Well, one easy way for me to describe that is to just look literally in this first table, my observed values were 60, my expected values were 46, right? So I'm just going to take the difference between those two. That's equal to 60 minus 46.8. Okay, it comes out to 13.2. The bigger the difference, the more likely it is that there is an association here, right? We'd expect a small difference, not big differences. Okay, so the next cell, 70, is going to be equal to 70 minus 83.2. Okay, the next cell, you're starting to see something interesting happening here, right? Next cell is 120 minus 133.2. And the next cell is 370 minus 236.8. Whoops, something went wrong there. Equals 370 minus 236. Yeah. Is that right? What happened there? Oh, I should have got 250. What am I doing? I went into the wrong cell there. That's C4. Right? That's better. Okay, so now these differences represent the magnitude of the difference between each corresponding cells in my observed table and my expected table. If I add them all together, what's going to happen? It's going to be zero. It's always going to be zero because, as one cell increases in value, it's the same. They're built on the same number of people, the same occurrences. So the differences are going to cancel out. So in statistics, a lot of times, what do we do to get rid of that difference so we can measure a magnitude of variability? We square it. Okay, so let's take these values and square them. Okay, so I'm going to go in here and I'm going to, it's an easy way for me to do this. Well, I'll tell you what, I'm going to make a new table. Okay, I'm going to go over here. I'm going to say that's equal to this squared. Okay, is equal to this times itself. Is equal to this times itself. And this is equal to this times itself. Okay, so now the problem with that is I've increased the variability by, by a square, factor of a square. So now I want to bring it back into the range of the variability that is really in these tables. So what I'm going to do is I'm going to go back into each one of these cells that I've squared, and I'm going to divide them by one of the values. And I'm going to divide them by the value for the expected value. So for this first cell, I'm going to take the observed value for cell 1 minus the expected values of cell 1, square it, and divide it by the expected value. Okay, so that becomes 3.72. Then for the second cell, I'm going to take the observed minus the expected for that cell, square it, and then divide by the expected value, which is 83, I guess, right? Oops, did I put it? Click back in there. Divided by 83.2. Okay, and next cell, okay, divided by 133.2. And finally, the last cell, divide by the expected value, which was 236.8. Okay, I think I got them all right. Okay, so now I'm going to add all these together. Okay, and my total comes out to be 7.86. That is the value for my statistic, which we're going to call chi-square, right? Chi, Greek letter, big letter X with a square on it. That is going to be my chi-square value. The smaller that value is, the more likely it is that the difference is due to chance. The bigger that value is, the less likely that the differences are due to chance. And the less likely I will be to reject my null hypothesis and be wrong. What's usually the level of certainty that we want to achieve for most of our statistical tests? Right?
0.05.
Yeah, we want an alpha of 0.05. We want less than 5% chance of an alpha error when we reject our null hypothesis. So how do we know whether or not that chi-square value is large enough for us to reject the null hypothesis? Bingo. Let's go find a table. First, before we look at a table, let's take a look at what the chi-square value looks like. Chi-square distribution looks like. And here is the chi-square value. Okay, so now here's a whole bunch of chi-square distributions here. So now you notice that there's a bunch of different ones. What do you think? Why do you think there might be a bunch of different chi-square values? Why were there different values for T critical? Why were there different values for analysis? What degrees of freedom, right? So, sample size. In this case, our sample size, our degrees of freedom, is going to be based on basically, what numbers are we dealing with here? The numbers that we're dealing with here is really how many rows and how many columns we have. Right? Now, there's nothing that says it has to be a 2x2 table. In fact, you could have different levels of asbestos exposure and have more rows. You could have more different kinds of outcomes: lung disease, lung cancer, mesothelioma, so on and so forth. You could have other diseases. You could have your exposure could be hair color. You know, redheads, brunette. There have been studies, right? Susceptibility to like skin cancer for different eye colors and different hair colors and skin tones and so on and so forth. So your exposure could be, you can have a number of rows. You could have a number of columns rather than just 2x2, right? So the number of columns, number of rows are really going to be your degrees, going to determine your degrees of freedom. Okay, so for chi-square, the degrees of freedom are the number of rows minus 1 times the number of columns minus 1. So how many degrees of freedom we have here for a 2x2 table? 1 degree of freedom. Bingo. Okay, so let's find a chi-square table. And here conveniently is a chi-square table. Okay, you have them in your book as well. Okay, so degrees of freedom is equal to 1. Probability of exceeding the critical value. Okay, so let's see. Alpha is for 0.05. So what is our critical value for chi-square? 3.841. Okay. So have we exceeded the critical value for chi-square in this particular sample? We have, right? Right. We got 7.86. So if our chi-square is bigger than the critical value, it means our probability of an error if we reject the null hypothesis is less than 5%, less than alpha, right? So if we want it to be 99% certain, and alpha is equal to 0.01, what would be our critical value? Be 6 point, right? We would still reject the null hypothesis, right? What about if we wanted to be 99.9% certain, right? That would be and alpha is equal to 0.001, right? We wouldn't be able to reject the null hypothesis for that. Kind of in a backwards manner, we determined that our p-value is somewhere between 0.01 and 0.001. Right? When we use SPSS or we use R, you'll actually be able to determine what that p-value is. Right? From the table, we can just decide. We can kind of bracket what the p-value is if we wanted to, but essentially what we're really interested in knowing whether or not we can reject the null hypothesis. Okay. Is it blurry? Is that what it is? I see people squinting. Okay. Yes. Yes. Hang on a second. What's this? Why did that come up now? Goodness. Okay, let's go back over this. In fact, the formula is right below it. I got the chi-square by taking each one of the cells, right? In other words, this is what I would have expected those cells to look like if people that were exposed to asbestos, and people that were not. Did I do something wrong here? Oh, I'm sorry. Okay, people that were exposed to asbestos, people that weren't exposed to asbestos were getting lung disease at the same rate. In other words, 26%. First thing I had to do was create this table of expected values. Okay, and I did that by saying, oh, well, 180 overall, 130 out of 500 people had lung disease in this population, which is a prevalence of 26%. So I would expect if I sample 180 people who have asbestos exposure, but it's not causing lung disease, I would expect 26% of them to have lung disease. So 180 times 26% is 46.8. And that would leave 133 that don't have lung disease. Okay, 320, I'd expect the same rate. 26% of 320 is 83.2, and this would be the remainder of the people. So now I want to see if the differences between what I really observed and what I would have expected if there was no association, if they're really different enough for me to say with the level of certainty that I want, that the association is not due to chance, so I can reject the null hypothesis, right? So the way I do that is I take each cell, I took 60 minus 46.8, I just want the difference. I squared that difference, right? And then I divided it by the number that's in the expected values, okay? What does that do? That, first of all, makes everything a positive number, and then dividing it by the expected value brings the number back into the range of numbers that we're dealing with. Otherwise, we would get a chi-square value that's like 1,000, right? So I do that with each cell. This cell, this cell, this cell. I do it with each one of them. I take the four numbers that I wind up with, which are here. I add them all together. It comes out to 7.86. And then I take that number, determine my degrees of freedom, and look up what my critical value of chi-square is. Okay. Yes. Yes.
Were you given the prevalence on the top?
The prevalence?
Yeah.
We weren't given it. The way I calculated. How did I calculate it? Well, everything went away there. Okay, so I took 500 people, 500 Navy randomly selected workers from the Brooklyn Navy Yard in the 1950s and 60s, high level of lung disease, heavy smokers, heavy drinkers. Many of them had significant exposure to asbestos. I took 500 randomly selected 500. I found that 180 of those 500 it reported a significant asbestos exposure. 320 didn't report a significant asbestos exposure. Of the 180, I tested them. 60 had lung disease, significant lung disease. Out of the 320 that weren't exposed, 70 of them had lung disease, right? So more of them had lung disease, but that was out of 320, out of a larger group. So what was the rate at which overall that they got lung disease? The overall rate is 130 out of 500. In other words, just looking at that population, what was the rate that they got lung disease? Well, I can derive that from this same sample, right? Overall, just by randomly selecting 500 people, I found 130 had significant lung impairment, right? And that was 26%. Then I used that 26% to figure out what would I have gotten if I selected 180 people that had asbestos exposure, 320 that didn't have exposure. How many of those 180 would I expect to have lung disease if asbestos has no influence on this? Well, it's the same 26% for both groups. I would expect 26% at 180 and 26% at 320. That's how I constructed my observed value table. Okay? Makes sense. Any other questions on that so far? It's pretty straightforward, right? I mean, it's not even really hard algebra at this stage. Okay, well, we're cheating a little bit, right? Because we didn't calculate the odds ratio for the confidence interval for the odds ratio. That could get a bit more complicated, but we're going to use SPSS, I think, or R, or whatever statistical program that you might want to use to do that. So, in fact, maybe now is a good time to like delve into SPSS or the community health survey. Now, why would